All right, guys, back into section 1.2, all of these properties. Let's dig into the rational functions a little bit more. We have not yet talked about horizontal asymptotes, end behavior, and range, how those kind of all go together with these. So let's take a look. Here's an example. Think about the function f of x equals 10 over x. And let's evaluate it at a few different x values. You know, imagine we had a table with some x values. What would 10 divided by these x values get us? So the 10 divided by 0, if it's f of 0, right? 10 divided by 0, of course, is undefined. And that is why we're getting this vertical asymptote at x equals 0. Okay, remember again, anything that makes the denominator 0 is a discontinuous value, right? In this case, it's a vertical asymptote because nothing got canceled out. But what happens as we change x values? What is f of 0.1? So 10 divided by 0.1 is actually 100. And I'm just doing these on a calculator. 10 divided by 0.01 is 1,000. Okay, so what ends up happening is as we're getting closer, right, these are getting closer and closer to 0, you can see the y values are getting really, really huge. And that's why this graph is like, as you get closer to 0, the y values are just growing and growing and growing. But it's never going to quite get to the y-axis there because when x actually is 0, the function's undefined. Okay, and then what ends up happening is the x values get larger. Think about like f of 1 and f of 10 and so on. F of 1, right, 10 divided by 1, of course, is 10. F of 10, right, 10 over 10 is 1. So as we go farther out, as the x values increase, these y values are just decreasing and decreasing, okay? But they're never going to quite get to 0, right? 10 over x, if you think about that, as x gets bigger and bigger and bigger, the y values are going to approach 0, okay? Now on the other side, we would get some similar things, but it would just kind of change to having negative values, right? If you're dividing, if it's 10 over x and x happens to be negative, you're just going to get negative y values, and you can test a few points, but it would look like that. But what I want to illustrate here is this idea of a horizontal asymptote as well, okay? Because the y values are approaching 0 in the long run, but they will never quite get there. Right? Imagine again, put in a huge number for x, 10 divided by 600 million, right? It's going to be close to 0, but it's never going to quite reach 0. Okay, so let's talk about how do we get these horizontal asymptotes, talk how everything kind of relates to each other. Let's add one more thing while I'm thinking about it. Oops, that wasn't what I wanted to do. Again, just remember in this case, let's see if we have room to do it on here, the domain of this guy, since we have the vertical asymptote at 0, the domain is all numbers except 0. Okay, like we did in the previous section. Now the range, we're going to see, the range is very closely related to the horizontal asymptote. Right? Think of a horizontal asymptote as like a wall, or that it's blocking a certain y value. Right? We see that yellow dashed line we drew. The y's are never going to equal 0 in this problem. But we see up top here the y values can be anything above 0, right? And then this piece of the graph is going to include all the negative y values. It's just never going to quite go through 0 because we have that horizontal asymptote there blocking it. Okay, so let's dig in, go through a couple examples, and try and get more comfortable with these ideas. All right, so when we're thinking about horizontal asymptotes, okay, and again, just get a picture in your head, right? Horizontal asymptote is going to be something, you know, like this maybe. What it's going to do is it's going to block the graph from going through a certain y value, so it's very closely related to the range, okay? If you know the horizontal asymptote, you'll be able to find the range. So the trick to finding the horizontal asymptotes is by looking at the degree of the function, okay? And the degree of the function is just the highest exponent. Okay, and just by knowing some things about those, we will be able to tell where the horizontal asymptote is without even really needing to make a graph. Now you can always graph, you know, and it helps sometimes, but it's not always really easy to see the horizontal asymptotes. Sometimes it's much easier just to look at the expression itself and do the process we're about to do. So since we're talking about rational functions, we're going to have a numerator and a denominator, so they are each going to have their own degree, and they may be different, okay? So I'm just going to use abbreviation. D is going to be the degree of the denominator, and n will be the degree of the numerator. And let's look at an example. There's 3 possibilities of what can happen, and there's a way to find the horizontal asymptote for each of those. Okay, so first example here, okay? In this case, the degree of the denominator, okay, take a look at the expression. The denominator has an x to the first power, so its degree is 1, while the numerator doesn't have an x, okay? So the denominator's degree is greater than the numerator's degree, right? It's larger in the bottom of the fraction, okay? In that case, that's similar to the one we did in the warm-up, where if you take a look at the graph here too, you can see this thing is approaching in the long run. See, these branches are going to 0, and that's again because the denominator is just going to get bigger and bigger and bigger. And if you think about a fraction, if the denominator is getting bigger and bigger and bigger, it's going to force the value of the fraction to get smaller and smaller and smaller, and eventually just approach 0. So the rule is, if the denominator's degree is larger, the horizontal asymptote is always y equals 0. Okay, and what that means for us is that the range then, okay, let's first write, so the horizontal asymptote, because of the degrees, is y equals 0. That means the range is all y values except 0. Okay, and if you were writing that as inequality notation, you would say it goes from negative infinity up to 0, don't include 0, union 0, again not including 0, to infinity. Okay, remember the parentheses mean that 0 is not included. Okay, so that's the horizontal asymptote and the range. Domain, just as a review, right? Domain deals with what makes the function undefined. So in this case, since it's a rational function, x plus 5 being in the denominator, right, cannot be 0. So if we wanted to solve that, we would get that x cannot equal negative 5. That's going to be the vertical asymptote. You see that on the graph right through here. That blocks the graph from going through that x value. Okay, so let's add one last thing. Let's talk about end behavior, right? End behavior is asking, what is the graph doing on the ends? So when you find this horizontal asymptote up here, you're basically saying what the graph is approaching on the ends. Okay, that's the exact same thing that end behavior is asking. So the good news is end behavior, horizontal asymptote, and range are very closely related. So let's just remember how to write this. We're going to say as x goes to positive infinity, what is y doing? Okay, so as x goes to positive infinity is over here on the right side. The y values are approaching the horizontal asymptote, which value was 0. Okay, on the left side of the graph, right here, as x goes to negative infinity, the y values are also approaching the horizontal asymptote of 0. Okay, so this tells you a whole bunch of things. It tells you the horizontal asymptote, obviously that's what it is, but it also then relates very closely to the range and to the end behavior. Okay, last thing on this graph, the increasing and decreasing. Again, as you read a graph, you always read from left to right. So if we start way over here, this graph, the y values are getting smaller and smaller and smaller and smaller. Then you hit the vertical asymptote at 0, but as soon as it picks back up, the y values again are getting smaller and smaller and smaller and smaller and smaller. They're even decreasing as we go out here. So this thing is decreasing over its entire domain. Okay, let's take a look at another example. Example 2. The second possibility is if the numerator has a higher degree than the denominator, like this one does. Okay, if that happens, then the function has no horizontal asymptote. Okay, and the reason why is, again, let's just look at the function real quick. Notice the degree of the numerator is 2, while the denominator's degree is 1, right? So the numerator has a higher degree. So what ends up happening in that case is that if you have a fraction, when the numerator is higher, the whole fraction is just going to grow and grow and grow to infinity. So it's not going to have like a cap or like a floor, like a ceiling or floor, like a horizontal asymptote. Okay, this graph is just going to keep going up and up and up. This portion is going to keep going down, down, down. So there's nothing that it's going to level out to. Okay, it's actually called a slant asymptote, which is something we don't really need to worry about. But it does not have a horizontal asymptote. Quick review though, it does have a vertical asymptote, because again, the denominator, if x were 1, that would cause our fraction to be undefined. So that's why we have a vertical asymptote there. Okay, end behavior on these, since it has no horizontal asymptote, just look at the graph. As x goes to infinity, okay, the y values over here, the right side, are just growing to infinity as well. And on the left side, as x is going negative over here, the y's are going to negative infinity as well. Okay? All right, what if the degrees are equal, right? That's the only other option. We saw one where the numerator was bigger. We saw one where the denominator is bigger. So if they're equal is the only other possibility. Okay, and if you take a look at this graph, we can see it appears there is a horizontal asymptote. The trick is the horizontal asymptote is the ratio of the leading coefficients. Okay, and we'll talk about that and show what that means. So I'm running a little bit out of space here. Okay, so what I mean by that, the ratio of the coefficients, right? And first off, notice they are both x to the second power, right? So they're equal degrees. Now their coefficients are what we look at. It was 1x squared over 1x squared. So the ratio is 1 over 1, which of course equals 1. Okay, right here, y equals 1. So let me move that down a little bit. The scale, I think that one was going by 2's. Yeah, so it's kind of down here somewhere. So that's the line y equals 1. That is a horizontal asymptote. Okay, that makes the range then, right? If that horizontal asymptote is there, the graph's not going to go through that value. The range will be all values except 1. Okay, as an interval again, it means from negative infinity up to 1. Don't include 1, but then right after 1 to infinity. Okay, now what about reviewing the vertical asymptotes and domain? Okay, let's get this function simplified a little bit. X squared minus 16 over x squared minus 9x plus 20. If we factor that, right, the numerator is the difference of perfect squares, x plus 4, x minus 4. The denominator is factorable, x minus, what is that, minus 5, and x minus 4. Okay, so that's going to tell me right now that the domain, right, the two values that would cause the denominator to be 0 is that x cannot be positive 5 and x cannot be positive 4. Okay, because each one of those would cause this to be undefined. However, which one's a vertical asymptote? Since the x minus 4 cancels out, x equals 5 is the vertical asymptote, and the other discontinuity at x equals 4 would become a hole in the graph. Okay, so all that stuff needs to be kind of simplified out because there are two discontinuities, one hole, one vertical asymptote. Okay, last couple things on this one. The end behavior again, as x is getting larger to infinity, the y values are approaching the horizontal asymptote of 1. And the same thing on the left side. As x is going to negative infinity, y's are approaching 1. Okay, and then finally, as far as increasing or decreasing, this thing again, as you read it left to right, is very similar to one of the first ones we did. The y values are slowly decreasing, 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 and even when it picks up here on the other side of the vertical asymptote, the y values again are decreasing, decreasing, decreasing. So this thing is decreasing over its entire domain. And that's exactly how you can write it. It's just always decreasing. So therefore it has no minimum or maximums. If it asks for the extrema, it doesn't have any. Okay, so hopefully that helps. We can get a good chunk of the table completed and then kind of get all this stuff wrapped up together. All right.